Welcome back, everybody. In this video, we're continuing section 3.7, and we're going to start by taking a look at the behavior of a function's graph near its vertical asymptotes. So we saw in the last video that the vertical asymptotes basically look like this. The function is either going up towards positive infinity or down towards negative infinity on one side of the graph or the other. Our first examples we saw where the graph of, sorry, I don't want to make you dizzy, the graph of 1 over x and the graph of 1 over x squared. And a big difference between these two graphs is that while both have the y-axis as a vertical asymptote, the behavior on either side of the asymptote is different. That is, on 1 over x, it goes down on the left and up on the right. But on 1 over x squared, both sides it goes up. So what causes that? And how can you tell by looking at the formula whether it's going to go one up on one down or both sides up? So that's what this next part is about. Okay. All right. So it turns out that the behavior near the asymptotes is totally determined by the multiplicity of the factor in the denominator that corresponds to the asymptote. For example, in this function f, it's not its graph shown down here, x minus 2 is cubed, and so the 2 here, this thing would have a vertical asymptote at 2. This has odd multiplicity because the 3 is odd, and so that means that it will be up on one side and down on the other. For the x plus 1 squared, it's going to have an asymptote at x equal negative 1. But because it's squared, which is even, that means that it'll be either both up or both down. It's going to have the same behavior on both sides of the asymptote. So when it's odd multiplicity, it will be, remember the 0 of the denominator gives you the vertical asymptote. The odd multiplicity will come if you have, it will lead to the behavior being one side up, the other side down. So the behavior will be split. If the 0 is of even multiplicity, you're going to have either both sides up or both sides down. It will take you a little bit more analysis to decide, okay, which one is it going to be, but you know, you will know at least, is it going to be both up or both down. Okay, so then let's take a look at this function f, which is 2 over x plus 4 times x minus 3 squared. This thing is going to have a vertical asymptote at x equal negative 4. And it will also have one at x equal 3. But the behavior for the two asymptotes is going to be different. For the one at negative 4, so there's one at negative 4, and then there's one at positive 3. The one at negative 4, I know that this has odd multiplicity, so it'll either be left side down, right side up, or maybe it will be left side up, right side down. We'll have to do a little more work to decide which one it is. We can do that here in a minute, actually. And then for the one at 3, I know that this has even multiplicity. So it will either be both up like that, or it's going to be both down because of the degree on those two polynomial factors in the denominator. So let's go ahead and figure out which it's going to be. Now's a good time, as any. So let's think about the x-intercepts, actually. Sorry, subject change. The x-intercepts are going to be the points where this thing crosses the x-axis, right? And so that's going to happen when f of x is equal to 0, right? F of x equals 0. So this thing, 0, is equal to 2 over x plus 4 x minus 3 squared. So based on what you know about fractions, the only way that a fraction could be 0 is if its numerator is 0. And 2 is never equal to 0. So this thing is never going to equal 0. It has no x-intercepts. Okay. So it has no x-intercepts. So that's going to help us actually, because once we've decided whether the function is positive or negative on one side of the two vertical asymptotes, or the other, then we know basically the whole rest of the graph. So what I would do is just start with a particular value. So one of the values that you can use would be the y-intercept, right? Because we're going to eventually need the y-intercept too. So the y-intercept is f of 0. Notice we're not setting this equal to 0 now, right? We're plugging in 0. So f of 0 will be 2 over 4 times 9. That's 2/36 or 1/18, or a small positive value. Okay, so there's our y-intercept. Okay, so this is kind of cool because once you've done that one point, you basically are going to know what the whole rest of the graph is going to look like. This thing has no x-intercepts, right? Since it has no x-intercepts, it can't go down like that, right? Because if it did, then boom, you have an x-intercept. But we know that that can't happen. So it must go up towards plus infinity that way and that way, because it's not coming down and crossing the x-axis, right? Because there's no x-intercepts. So what does the rest of the graph look like? That is, over here, we need to decide which side, is it going to go up? Is it going to go down? What will it be? At 3, we saw that this had even multiplicity. So that means it's going to have to go up towards positive infinity. On the other side of -4, it has to go down towards negative infinity. It can't be up towards plus infinity because that was a 0 of odd multiplicity. All right, so there's basically a rough sketch of our picture. We saw that calculating 1 point was enough to get it done for us, and knowing the multiplicity of the zeros. Okay, so we'll do plenty more graphs as we proceed, but I wanted to do just one there. Okay, so to recap that briefly, the behavior near the vertical asymptotes is dictated by the multiplicity of the 0 that gives you that vertical asymptote. If it's a even multiplicity, then it'll be both up or both down. If it's odd multiplicity, it's 1 up, 1 down. Okay, the next part is about horizontal asymptotes. Okay, so horizontal asymptotes are going to be horizontal lines. And so their equations will look like y equals b. The line y equal b is a horizontal asymptote if the function values, if y approaches b as x approaches either plus or minus infinity. So here, the graph on the left, the red graph is increasing towards our dashed line as x increases without bound. The one on the left, as x decreases towards negative infinity, our graph is heading towards that dashed line. A big difference between vertical and horizontal asymptotes is that while a graph will never cross a vertical asymptote, it's possible for the graph to cross a horizontal asymptote, okay, as you can see in the picture on the right. All right, so we want to figure out how to find out the horizontal asymptotes for a function. And fortunately, that's not hard. So it turns out we're going to do this kind of by doing some algebra first, and then we'll see kind of a general rule that follows from that. Okay, so let's try 3 examples, because there's basically 3 different kinds, as you will see. So here we have this f, which is 2x plus 1 over x squared plus 3x minus 8. Take a look at the function and see what is the highest power of x you see in it. Okay, you should see the x squared right away. So what we're going to do is we're going to multiply the numerator by 1 over x squared and the denominator by 1 over x squared. Okay, the reason why is going to rewrite our function f in a format that is going to be easier for us to understand. Okay, notice that the red fraction is worth 1, which means that we're not changing the value of our function at all. We're just changing its look. So distribute. 2x times 1 over x squared will give you 2 over x. And then 1 times 1 over x squared will give you 1 over x squared. Okay, down here on the bottom, we're going to multiply by the x squared plus 3x minus 8. X squared times 1 over x squared will be 1. 3x times 1 over x squared will be 3 over x. And then negative 8 times 1 over x squared will be minus 8 over x squared. Okay, so now for horizontal asymptotes, this is kind of like end behavior for a polynomial. We want to know what's happening as x goes towards negative infinity or x goes towards positive infinity. So what is happening to the function there? This is basically the end behavior for a rational function. So we're talking really, really big values of x. So here, picture putting in a giant size value of x. Here, 2 divided by a million, small number. 1 divided by a million squared, even smaller number. So this numerator is going to get really, really small. It's going to be nearly 0. Okay, and then the bigger that x gets, the closer to 0 it will be. Down below, 3 over x is going to be like 3 millionths or 3 billionths, right? Super tiny number. 8 over x squared, also super tiny. So the second two fractions will be nearing 0. Our overall denominator will be nearing 1. Okay, if you have fractions that are nearly 0 divided by numbers that are nearly 1, that overall is going to approach 0 as x increases without bound. So for this one, our asymptote would be the x-axis, y equals 0. Okay, so let's try that again. Here we have 5x cubed plus 4 over 2x minus 7. So again, our highest power of x we see here is going to be x cubed. So we're going to divide by, or multiply both sides by 1 over x cubed. Okay, so then once again, let's distribute. 5x cubed times 1 over x cubed will be 5. And then we'll have plus 4 over x cubed. Okay, down below, we have 2x times 1 over x cubed. That will be 2 over x squared minus 7 over x cubed. Okay, so now let's think about what's happening to our numerator and denominator. Remember, x is getting really, really big, right? If x is getting really big, like a million, a billion, a trillion, right? Then cubing it makes it even more huge. 4 divided by that, 4 divided by a really big number is really tiny. So the numerator here is getting close to 5. So it's nearly 5. If you like, take and plug in some numbers for x, and you'll see that 5 plus 4 divided by like a really huge number is going to be nearly 5. Down below, though, we have 2 divided by a big number. That's going to give us something nearly 0. 7 divided by a really big number. Again, something that's nearly 0. So down below, we're going to end up with something that is nearly 0. Okay, if you have numbers nearly 5 divided by numbers that are really small, nearly 0, you're going to end up with really huge numbers. So this is going to approach positive infinity as x increases without bound. Okay, so this one will have no horizontal asymptote. Okay, we have only one more of these, okay? And then we'll kind of summarize what it is we've gotten. All right, so here you'll notice that the numerator and denominator both have degree 2. So we're going to multiply by 1 over x squared on both. Okay, and so then that 1 over x squared, as before, we're going to distribute. 6x squared times 1 over x squared will be 6. 3x times 1 over x squared will be 3 over x. And then 4 over x squared to finish. Okay, down below we have 7x squared times 1 over x squared. That will be 7. Then 4x times 1 over x squared will be 4 over x. And then lastly, we'll have negative 1 over 3x squared. So then, once again, we need to think about what is happening to our fraction here as x is either increasing or decreasing without bound. So each of the fractions that have x in the denominator are nearing 0, right? So the numerator overall is approaching 6, and the denominator overall is approaching 7. So that means that our, horizontal asymptote will be y equals 6/7. Okay, so that's our horizontal asymptote. If you're unsure or skeptical about any of this, you should draw the graphs of these on the computer, or just try plugging in some values of x for each of these and calculating what happens to the function values as x gets really, really large. Okay, so let's see if we can just kind of summarize what happened here. So we saw that on this one, the degree of the numerator was less than the degree of the denominator. So as x raced off to infinity, in a way, the denominator won, right? So the denominator got bigger much faster than the numerator did. So overall, the fraction approached 0. In the second one, the numerator was a bigger degree, and so it grew faster than the denominator, and so it didn't settle down to a finite value. There was no horizontal asymptote. For the last one, we saw that we got y equals 6/7 because the numerator and denominator basically grew at the same rate. They both had degree 2, so they grew pretty much at the same rate. All right, so we can summarize what we found out in this little table right here. So let's say that we have this rational function. Here they called it r of x instead of f of x, but that's okay. And it's a quotient of two polynomials. Notice that the numerator has degree n, like never, and the denominator has degree m, like monster. And so the horizontal asymptotes you get by looking at those degrees, that m and n. Okay. If n is smaller than m, that is the degree of the top is smaller than the degree of the bottom, then the x-axis makes a horizontal asymptote, the line y equals 0. If they have equal degree, if the n is equal to the m, then you get the quotient, y equals the quotient of those two leading coefficients. If the numerator degree is bigger, then there's no horizontal asymptote. Okay. So let's just kind of use that kind of general guideline to help us find asymptotes, horizontal asymptotes for these. So for this one, it's degree 2 in both the numerator and denominator. So that'll be basically part C in this little box here. It'll be y equals 3/4. Okay, notice that I'm not just writing 3/4. Okay, remember that just like vertical asymptotes, horizontal asymptotes are lines, and so you need to write down the equation of a line. So here it's y equals 3/4. Okay, for this one, the degree of the numerator is 1, degree of the denominator is 2, and so the bottom wins, so it will be y equals 0 for our horizontal asymptote. Okay, next one, the numerator degree is bigger than the denominator degree, so this will have no horizontal asymptote. Okay, just by taking a look at the degrees. In a way, finding horizontal asymptotes is easier because all you got to do is look at those degrees of the two polynomials and compare them. Is it going to be 0? Is it going to be no horizontal asymptote? Or is it going to be just that quotient? So in a way, it's a little less work than finding the zeros of the denominator. All right, so these examples, it said find all of the asymptotes for these functions. So these have been the vertical asymptotes. Just for practice, let's go ahead and get all of the vertical asymptotes as well. So I'm going to do those in green. So this will be vertical asymptotes. Okay. So to contrast, again, the vertical asymptotes will come from the zeros of the denominator. So let's see, for this one, we have 4x squared minus 9 equals 0. So 4x squared equals 9, x squared equals 9/4. So then x will equal plus or minus 3/2. Another difference between vertical and horizontal asymptotes is that you can have multiple vertical asymptotes, but you'll only ever have one horizontal asymptote. So take a minute and think about why that has to be true. What would it be like if you had multiple horizontal asymptotes? Okay, so these are going to be our vertical asymptote. Okay, here x squared minus x minus 6. Let's go ahead and set that equal to 0. And this one, luckily, we can factor. I feel like we did this one already today. Maybe we did, maybe we didn't. All right, so that will be x squared minus x minus 6. No, it isn't. Yes, it is. Okay, so x equals 3 and x equals -2. All right, last one. For this one, I'm not going to bother checking to see if there's a 0 of the numerator, okay, that matches one of the zeros of the denominator. Let's just take a look at that denominator, 2x squared plus x plus 3. So then let's check and see. This thing is quadratic. I don't see, or maybe we don't see how to factor this, so we can just jump straight into the quadratic formula for this. So that will be -1 plus or minus the square root of 1 minus 4 times 2 times 3, and that's over 4. So taking a look at this, we can tell right away that that radicand is going to be negative, and so there's going to be no vertical asymptotes, okay, because of the fact that our radicand is less than 0, which would give us complex solutions. So that's not going to give real zeros. Okay, so that was fun. So just another couple of examples about finding horizontal asymptotes. As you saw, they go by pretty quickly. So here in the notes, I've just repeated the same table, so you don't need to maybe attempt to write that down again. All right, so let's try a couple of these. I've picked out a few. So for 34 here, it's 3x squared in the top and x to the 4th in the bottom. Here, the degree of the bottom is bigger, so it will be y equals 0. Okay. For 39, it's 6x cubed over 2x cubed. The leading terms are both x cubes, and so it'll be 6 over 2. And that's just y equals 3. All right, so that has been a couple of horizontal asymptotes. The vertical asymptotes, I think we've practiced enough of that. Okay. Let me know, though, if you have any questions. We'll do more. All right, so now we're ready to start tackling a graph of one of these things. Now we know a little more. So our function f looks like x plus 1, and that's over 2x minus 3. And so we want to apply some things that we know to start producing the graph. So first thing to do is to get any kind of vertical asymptotes. Okay, so that would be the zeros of the denominator will give us those. So x equals 3/2. So we'll have a vertical asymptote here. And then for a horizontal asymptote, numerator and denominator have degree 1. So it'll be the ratio of their leading coefficients. X plus 1 has a leading coefficient of 1. And so it will be y equals 1/2. Okay, so that will be our horizontal asymptote. And then let's get some intercepts as well. So the y-intercept will come from f of 0. So if you put 0 in for x, you're going to get -1/3. And then for the x-intercept will come when the numerator is 0. Remember, the denominator zeros give you vertical asymptotes. Numerator zeros will give you x-intercepts. So x plus 1 equals 0, x has to equal -1. So as points, that would be -1, 0 for the x-intercept, and 0, -1/3 for the y-intercept. Okay, and then now we're ready to start drawing the picture. So let me get some axes on here. There we go. All right. So it's a good idea to figure out some of this stuff before you try drawing the graph, right? So important points are at like 1s and 2s maybe. So we could just scale our axes to like 2, right? Maybe 3 in both directions. As long as you make the 2 number lines equally spaced, your picture will look decent. Okay, so let me put on those vertical asymptotes first. So they will be, there's only one, it was at 3/2. Okay, so let's draw that on. I like to write the equation of the asymptotes as well. So that was x equals 3/2. Our horizontal asymptote was at y equals 1/2. So we can put that on there. All right, so we have our 2 asymptotes, and then we're going to put down our intercepts as well. So we had a x-intercept was at -1, 0. And our y-intercept is going to be at 0, -1/3. Okay. All right, so that's what we've got so far. So we need to figure out how the rest of this graph is going to look. We know that the graph doesn't cross its vertical asymptote. So we need to think about where it will have to be. The only x-intercept we have here is at -1. So right here at this point, we need to think about where this is going to go. Could it go down here or could it go up? I know at this vertical asymptote, it's going to have to go towards positive infinity. The thing is that it can't go up towards positive infinity, because if it did, there would have to be another x-intercept in this interval, and there's not. So that means that it has to go down. Okay. And then there's only one x-intercept, so it has to kind of connect up to the x-intercept here, and then it will keep going up. I have more to do on that side in a minute. I'll finish that graph, half of the graph in a minute. So then over here, we got to decide again, is it going to go above or below? Which will it be? Taking a look back at our original function, 2x minus 3 had multiplicity 1, which is an odd number, right? And so that means that the graph will have to go down towards negative infinity. No, it won't. It'll have to go up towards positive infinity. How was I thinking? Because if it's odd degree, they have to be opposites. Okay, another way of seeing that is this. It was going to have to approach that horizontal asymptote. If it was going to be like this, then it would have to cross the x-axis once again to get towards that asymptote, and it doesn't. So it's got to be more like this. Okay, odd degree, so the behavior is opposite for the 2 asymptotes. All right, so now the thing is, the graph, we don't know, does it kind of approach that asymptote from below, or does it cross above and then kind of hook its way back down? That is it going to cross above and come down, or will it just kind of go like that? Okay, so we don't know which yet. So what you want to do is say, okay, will it ever equal its horizontal asymptote? And so that's going to take us a little bit more algebra. We'll do that right now. So we want to know, is f of x, which is x plus 1 over 2x minus 3, could that ever equal 1/2, which is the y value for that horizontal asymptote? So let's go ahead and set it equal to 1/2 and see what happens. So we're going to solve this equation for x, and that'll tell us where this black line is going to cross that red dashed line, if ever. So multiply through by 2x minus 3 to clear the fractions out. Okay, and then distribute. So this will give us x minus 3/2. That will equal x plus 1. right? Distributed to remove the parentheses. Now let's subtract x from both sides. If you subtract x from both sides, you have -3/2 equals 1, which is false, right? Since -3/2 never equals 1, that means that the graph never will cross that horizontal asymptote. And so it will just have to come up towards it from below in that way. Okay, so that does it for that. We can say a little bit more using the arrow notation to describe the behavior of our graph. We could say as x approaches -infinity, our f of x approaches -1/2 from below. As x approaches 3/2 from the left side, f of x approaches -infinity. That takes care of that branch. On the right side, as x approaches 3/2 from the right side, f of x will approach +infinity. As x approaches +infinity, f of x approaches 1/2 from the plus side. Okay, so that's our rational function graph. Looks pretty good. Let's see if we can try one more of those. All right, so here's some kind of summary of how to do one of these sketches, and then we're going to try it one more time. So factor the numerator and denominator to see what you have. Intercepts, x-intercepts are from the zeros in the numerator, and the y-intercept you get by evaluating f of 0. Vertical asymptotes come from zeros of the denominator. Horizontal asymptotes come from that procedure that we followed by comparing the degrees, and then based on this, sketch the graph. All right, so let's try it once more. So here the function is going to factor as the numerator. There's not a lot to do there. The denominator, it will be x minus 1, x plus 1. All right, so now intercepts. So y-intercept first will be f of 0, which is 0. So this one is going to pass through the origin. And then for x-intercepts, it's going to be the same. Okay, if it passes through the origin, and there's no other one. Okay, so asymptotes. So for horizontal asymptote, comparing the degrees, they're both x squared in the numerator and denominator, and so that will be 2/1. So y equals 2 by comparing those degrees of the numerator and denominator. The vertical asymptotes will come from the zeros of the denominator, so that will be at x equal 1 and x equal -1. Okay, so we have enough to start drawing this. All right, and again, use kind of the interesting points to decide how to scale this thing. So I'm seeing really zeros, ones, and twos for the numbers here. So let's just mark it up to like 3 in all directions. And then I like to put on the asymptotes first and then kind of build it up around the asymptotes. So the vertical asymptotes were at -1 and 1. And then I like the equations on there. Horizontal asymptote was at 2. So the line y equal 2 will make our horizontal asymptote. And then we need to think about maybe some intercepts next. So this one, it passed through the origin, right? That was the only intercept that it had. Okay, And then for the two asymptotes, the vertical asymptotes, the multiplicities were both 1, which is odd, so the behavior is going to have to be opposite on either side. So we need to think about where to kind of begin drawing the graph. So the only point that we have is passing through the origin. So we have to decide from here, let's go kind of in the positive x direction. So is it going to go up or down? So one thing that we could do is see, okay, is it going to ever cross its horizontal asymptote? So once again, let's set our function equal to its horizontal asymptote. So that's 2x squared over x squared minus 1. Will that ever equal y equal 2? So multiplying the clear fractions out, we'll have 2x squared is equal to 2x squared minus 1. Multiplying the clear parentheses, 2x squared equals 2x squared minus 2, or 0 equals negative 2. And that's false, right? So it's never going to cross its horizontal asymptote. So how does that help you? That means that I know it's not going up like that. Because if it was going up like that, it's crossed its horizontal asymptote. And we just showed that it doesn't. So that means that it has to go down. Part of what's fun for me about doing these graphs is that little bit of reasoning about deciding about how it's going to have to be based on what we figured out. All right, so that part has to go down. And we know that the behavior is going to be opposite on opposite sides of the asymptotes due to the fact that the multiplicity is odd on both. So that means it has to go up on this side, and I know it never crosses its horizontal asymptote. So it's got to look like that. Okay, and then for this one, the 0 for the numerator has multiplicity 2. So there's going to be no sign change here. So that means that when x is negative, in between 0 and negative 1, it's going to again be negative. So it's going to have to come down again. And then once more, it will be up on that side due to the fact that the multiplicity is odd for that one asymptote. Okay. All right, so that's another example. So we have one more of these to try, and then we'll go from here. So for this one, take a minute and do as we did for this last example. Write down the asymptotes, and then the intercepts, and then build the grid, and then we'll do the graph part together. All right, so I found the y-intercept by evaluating the function at 0. We get negative 1/4. There's no x-intercepts because the numerator is never 0. The horizontal asymptote was y equals 0. The vertical asymptote, which again we got from the zeros of the denominator, that works out to be x equal 2 and x equal negative 2. So let me start by putting all those asymptotes on our graph. So I'm starting with the vertical ones. We'll have x equals 2 and x equals negative 2. The horizontal asymptote was y equals 0. That's just our x-axis. So there's that. And then there was no x-intercepts, but we do have a y-intercept of negative 1/4. Okay, so it looks like that. All right, so then once again, we've got that. We want to think about what the graph is going to have to look like. I know that there aren't any x-intercepts, and so it can't go up towards positive infinity on either side of these, so it's got to be down for both of these because there was no x-intercepts. And then for each of these zeros for the denominator, they had multiplicity 1. So that means the behavior on the other side has to be opposite. So they'll have to go up towards positive infinity for both. Okay. All right. So that does it for this graph, and that does it for this video. In the next video, we'll have more examples of rational functions to play with.